Hello everybody and welcome to the second part of simulation of wing motion using OpenFoam. In the first part we treated the mesh generation using snappyHexMesh 3D in 3 dimensions. In this part we will process the simulation using SimpleFoam on 2D dimension wing. So let's go and see the generated mesh that we already have done in using snappyHexMesh in the first part. So I'll just visualize it, PimpleFoam. So this was our mesh with all these boundaries. I want to show you boundary by boundary because this will be helpful in order to generate the 2D dimension model for the SimpleFoam simulation. So let's start with the inlet. So this is the inlet, this is the outlet, top and bottom, the wing of course, then the symmetry front, it's the front here, the front of the geometry, then the sim back is the back of the domain. So here we have a 3D domain because if we do a clip right here, clip apply, then we'll visualize edges, you can see that we have, I'll choose here all the mesh parts. So here you can see that in the Z direction we have more than one cell, so our discretization is done also in the Z direction, so we have 3D case. So now what we need to do is to go and extrude a patch from this mesh in order to get 2D case. So we will go here in wing motion and the system, extrude mesh, and we will extrude a patch. Construct from a patch the source case. He will go and look for this he will go and look for this folder. So it's wing motion, snappy. Okay, so in this case it will look, in this case, wing motion snappyHexMesh. Then the source patch will be the symmetry plane, the front symmetry plane. I showed you, I'll open it again. So we will extrude the sim front, so this patch with edges, so we will extrude this patch. Then the exposed patch name is the patch for the back will be the sim back, so will be this. Then this is the model, and the number of layers, of course we need to specify it's just one layer in order to get the 2D case, the 2D model, because in 2D we have only discretization following one layer in the Z direction. This is the principle in OpenFoam, in fact. So this is the thickness and other parameters that you can set following your needs. So let's now extrude our mesh, wing motion, simple, we will go here and run Extrude Mesh. So it's done. So here we have our mesh, our 2D mesh, but before running the simulation we need to name our patches, our created patches. So we have here a dictionary in the system folder named create patch dict. In this file we are creating 2 patches. So we are naming the front and the back. For type, of course it will be empty because we are in 2D. Then it will be constructed from the sim back and the sim front already extruded in this file. So we will run create patch. So now we extruded the mesh, then we created 2 patches, the front and the back of the simulation. So let's now run the PimpleFoam. We have here our polymesh. Let's run only the first one and keep this .org. PimpleFoam, apply. Then here we have our surface. So now I'll do the clip as we did for Snappy in order to verify if we have only one cell or more, in order to verify the 2D condition. So as you can see here, we have only one division following the Z direction, so we have in the 2D case. So here we have the Now let's go and verify the initial conditions used in this case. So we have here the include. So in this case, in this tutorial in OpenFoam, they are using the include feature, which is we are putting our informations here. For example, the initial conditions. We are creating a file named initial conditions, then we are storing our variables. For example, the flow velocity is equal to 100, then the pressure 0, turbulent kinetic energy 37, and the turbulent omega 32. Then here in U, instead of for example saying that the internal field is equal to 100,000, we are just calling using this dollar, and it will point out this value using the initial conditions, since we already mentioned that we should go to include initial conditions. So the same thing for the inlet. So the inlet is already fixed here, fixed inlet with fixed value, and its value is equal to internal field, and the internal field is equal to flow velocity, which is 100,000. Then for the outlet will be depending on the inlet, and the wing it's not moving. In this case we have only moving wall velocity is equal to 0, 0, 0. Then for front, back, top, bottom patches, it's empty. For the front and the back, it's empty. Then the top and the bottom, we are choosing this type since we have kind of continuity in the top and the bottom. To keep this kind of feature, it's like our domain is continuous and the flow mustn't be impacted somehow if we are, for example, defining a wall or something else. So it's better to define a slip in order to get this like a slip boundary in order to get a flow slipping on this boundary. So this is the idea of the type slip. So now let's go and see the pressure. So the pressure is also the internal field is taken from here, 0. Then the inlet, 0 gradient, then front and back also empty, and slip. For the turbulence properties, so the key is equal again to 37, which will be it will be taken from here. K equal to 37. Then the front and the back as well. The wing will be we will apply a wall function on it in order to catch the turbulence near the wing. So the viscosity, turbulent viscosity for the wing and front, back, top, bottom, inlet and outlet, all the other boundaries, it's calculated. Then for the wing, we are choosing a function near the wall in order to get its value really precisely on the layers. Same thing here concerning omega, it's like key. We are taking the internal field from turbulent omega equal to turbulent omega here, and the outlet as function of the inlet. The wing also we are specifying omega wall function, and for the front, back, bottom patches it will be empty and slip as done previously. So this is the 0 folder, let's rename it 0. Okay, then for constants we have here, we have our mesh, that first. Then we have the transport properties, where we are precising that our fluid is Newtonian. Then the viscosity is equal to 1 multiplied by 10 minus 5. And this is the unit of the viscosity. It's m2 by per second. And for the turbulence model, it's RAS. The model is K omega SACT, and for the turbulence it's on, and printing coefficient also on. Then in system we've already create patch, extrude mesh. So for control dict it will be the solver here, SimpleFoam, starting from the latest time and time, the delta t equal to 1. Then here we are adding a function object in order to get the forces applied on the wing. So we are specifying this is the name of the function object, forces. Then its type is forces. It's taken from this library. We should mention the libraries. So it will be written each time step, and its interval will be written in folder each 10 time steps. Each 10 time steps. For the patch, it's wing, since we want to compute the forces applied on the wing. Then for rho, it's rho env. The rho env is equal to 1 because we have air, and the density of air is equal to 1. And here we have the coefficient direction, so this is the attack. This depends on the attack angle of the wing. So here we have the schemes. We have steady state since we are using SimpleFoam, and these schemes, it's by default done like this. In preference, just keep it like this unless you have problems in conversions. So in the FV solutions, it's the solver of each variable, then the tolerance, the relaxation factors of the variables included in this simulation. So now let's go and start our simulation. We will run it using solver SimpleFoam. So it exists because we have this including only polymesh. We don't have the initial condition. So I'll rename it dot mesh, for example. Up. Oh, sorry. So I need to copy this polymesh in this constant. So now it's okay. I'll remove this folder. Then we will wait until it's done. It will go until 3000 iterations following the control bits file. So yes, the end time will be 3000, so we will wait until the 3000s. We can check the forces because it will be written each 10 times step. So here we have the forces of pressure, of viscosity, and porous forces, and also the moments, the applied moments. So here we can get the evolution of the forces following our iterations. So we have 3000s. It's already done. We can now visualize our case. Apply, go into the last time step, and seeing the velocity. We can visualize the streamlines of velocity using point source. I'll increase the number. Okay. Then I'll increase this the sphere radius in order to get more information. I give it 1 or more, perhaps 1, 2. Then here I'll keep it on. I'll just reduce the opacity. Okay, so the stream tracer is here. Perhaps it's the radius 2. Okay, then here we have more extended streamlines. We can do, I think, 2, 2. It will be great. Okay, number of points, I'll increase more to get more. So here we have more streamlines. I'll mask the sphere. I prefer this color. So we can as well, I keep this on solid color. So here we have the stream tracer of our flow. We also have all the information here in the spreadsheet view. We can as well visualize the vectors and all the information we want to study. In this case, in the fourth part, after the PimpleFoam simulation, I will show you how to post-process the forces, because here we have a file, we have all the evolution of forces with time steps. I will show you how to put this data into graphs in order to get a clearer idea about the evolution of the forces applied on the air under this wing. So this is all for this video. See you in next part using the PimpleFoam into the simulation of wing motion. Thank you for your attention and see you soon.